In this video, we're going to look at another example of separable differential equations. So the question here is to find the family of curves that intersect every cubic function of the form y is equal to cx cubed at right angles. This is also known as an orthogonal trajectory. So we start by finding a differential equation that is satisfied by the cubic function that we're given, y is equal to cx cubed. It's only natural to differentiate this expression to obtain a derivative because after all, differential equations involve derivatives. So differentiate both sides, we get dy dx is equal to 3c x squared. Now let's get rid of this constant c so we only have x and y. So we can solve for c, we get c is equal to y over x cubed, and substitute it into here so that we can have a differential equation just involving x and y. So we get dy dx is equal to 3 times c, which is y over x cubed, times x squared. Now x squared cancels with x cubed, giving us x in the denominator, so we get dy dx is equal to 3y over x. This is a differential equation that is satisfied by the family of cubic functions y is equal to cx cubed. Our goal is to find the orthogonal trajectory of this, find the family of curves whose tangent lines are perpendicular to the tangent lines of y equals cx cubed when they intersect. Alright, so now any curve that meets the cubic function y equals cx cubed at right angles must have slope of the tangent line to be equal to the negative reciprocal of the slope of the tangent line to y equals cx cubed at the point of intersection. So the condition that we need for perpendicular lines, perpendicular tangent lines, is m1, m2 is equal to minus 1. The product of the slopes is equal to minus 1. Now, we know that for y equals cx cubed, we found a differential equation that's satisfied by this family of cubic functions is dy dx is equal to 3y over x. Now the orthogonal trajectory of family of curves must satisfy dy dx is equal to, well, it should be the negative reciprocal of this. So it should be, just flip it and put a negative sign in front, minus x divided by 3y. And this is applying m1, m2, the condition for perpendicular lines. m1, m2 is equal to minus 1. All right, so what we have is dy dx is equal to minus x divided by 3y. This is a differential equation of the orthogonal trajectory. Now we're going to cross multiply and separate out the variables, put all the y's on one side and all the x's on the other side so we can integrate. 3y dy is equal to minus x dx. Integrate both sides. When we integrate the left-hand side, we get 3y squared over 2. The right-hand side, we get minus x squared over 2 plus constant k. Just reversing the power rule. So bring everything to one side and we get 3y squared divided by 2 plus x squared over 2. I should say bring x squared over 2 to the left-hand side. This is equal to k. This is actually the equation of an ellipse. So what we have is 3y squared over 2 plus x squared over 2 equals k. This is the orthogonal trajectory of y equals cx cubed. Orthogonal trajectory of y equals cx cubed. So let's choose c equals 1. So we just have y equals x cubed. And let's choose k equals 1. So we have the ellipse x squared over 2 plus 3y squared over 2 is equal to 1. And you can see we have a drawing here. So the ellipse, you can see from the drawing for these particular choices of c equals 1 and k equals 1, in this drawing it's clear that the tangent line to the ellipse at the point of intersection with the cubic function, the tangent lines are perpendicular to each other. And that's what we mean to say that the ellipse is the orthogonal trajectory of y equals x cubed. This was a fairly simple example. We're now going to do something a little bit more difficult. So we want to find the orthogonal trajectory of the exponential function y is equal to e to the cx. We start by differentiating it. So y equals e to the cx. Differentiate both sides. We get dy dx is equal to c e to the cx. Now let's get rid of the constant c and find a differential equation that is satisfied by y equals e to the cx. So we have y equals e to the cx. To solve for the constant c, we should log both sides. So log y, that's the left-hand side, and log of e to the cx. So we get log y is equal to, and log cancels e, we just get cx on the right-hand side. Solving for c, we get c is equal to log y divided by x. So we have dy dx is equal to c e to the cx, and this is equal to c times y, because y equals e to the cx. Now we have solved for c. C is equal to log y divided by x and times y. So now we have a differential equation that is satisfied by the exponential function e to the cx. Dy dx is equal to log y over x times y. All right, so this is a differential equation that is satisfied by the exponential function y equals e to the cx. Our goal now is to find the orthogonal trajectory of this exponential function such that the tangent lines intersect at right angles. So now, to find the orthogonal trajectory of y equals e to the cx, we apply the condition m1, m2 is equal to minus 1. Since the family of curves whose tangent lines are perpendicular to y equals e to the cx must have the slope of the tangent line to be negative reciprocal of the slope of the tangent line to the exponential function y equals e to the cx at the point of intersection. So what we have is y equals e to the cx and dy dx. We differentiated this and we solve for the differential equation that is satisfied by this exponential function. This is equal to y over x log y. Now we're going to apply m1, m2. Product of the slope of the tangent lines is equal to minus 1, the condition for perpendicular lines. So for the orthogonal trajectory, the differential equation becomes negative reciprocal of this quantity here, which is minus x divided by y log y. So just basically reciprocate the fraction and multiply it by negative 1. So now we have to solve dy dx. This differential equation is equal to minus x divided by y log y to find the orthogonal trajectory of the exponential function. Orthogonal trajectory. So we have to separate out the variables and carry out the integration. All right, so we have dy dx is equal to minus x divided by y log y. Cross multiply so we can separate the variables, put all the y's on one side, all the x's on the other side. We get y log y times dy is equal to minus x dx. And we have separated the variables. Now integrate both sides. On the left-hand side, we have the product of a polynomial, which is y, times a log function. So it's natural to apply integration by parts. Substitution method definitely would not work. So we're going to let u equals, we'll let u is equal to log y. Easy to differentiate. Differentiate both sides. We get du is equal to 1 over y dy. dv is equal to y dy. And integrate both sides to get v. v is equal to y squared over 2, reversing the power rule. And recall the integration by parts formula. Integral u dv is equal to uv minus integral v du. Let me label this by parts. All right, so what we have is on the left-hand side, we have u times v, which is going to be log y times y squared over 2, minus integral v, which is y squared over 2, times du, which is 1 over y, dy. On the right-hand side, this is very easy to integrate. Just reverse the power rule. We get minus x squared divided by 2 plus, let's say, constant k. Let's label this here. And all right, so now we get log y times y squared over 2 minus 1/2. Y squared divided by y, we just get y. Integrate that, we get y squared divided by 2 is equal to minus x squared divided by 2 plus k. Let's simplify this. We get log y. This is 2. Log y times y squared divided by 2 minus y squared divided by 4 plus x squared over 2 is equal to k. This is the orthogonal trajectory of y equals e to the cx. So it's the orthogonal trajectory of y equals e to the cx. That means the tangent lines are intersecting at right angles to each other. All right, so this is of course an implicit solution because we're not able to find an explicit function. We can't get y entirely as a function of x. We can't make y the subject. So this is an implicit solution of the orthogonal trajectory of the exponential function y equals e to the cx. All right, thanks.